Hello, everyone, and welcome back to episode 2 of Coffee Break, the show where we break down interesting topics all within the time it takes you to enjoy a few cups of coffee. My name is Clifford Swartz, and today I'm joined by two special guests. Firstly, to my left, we have Enrique Alleman. How you doing, Enrique?
Very well, thank you. Thank you for.
So, Enrique, you are a technical staff engineer with a passion for functional safety. Would you say that?
Uh, I love functional safety, definitely.
Me too. So, while Enrique and I get to enjoy the sweltering Arizona weather, our second guest is enjoying some cool weather all the way from Denmark. We have Jacob Lund-Larsen. How you doing, Jacob?
Hello, guys. How are you?
Good, I'm excited. So Jacob is our subject matter expert on functional safety. And we've brought together these two experts for your viewing pleasure. But before we dive into the presentation today, I'm going to throw it back to Wayne Freeman, and he's going to tell you guys how to participate with us today.
Hello, everyone. How are you guys doing out there? Enjoying your lovely coffee this morning?
For sure, absolutely.
All right. Very cool. Very
and my
cool.
hard hat, too.
Yeah. So, everyone, if you want to speak to these gentlemen and please ask questions. Get your questions ready. Post them in the chat. We're on LinkedIn. We're on Facebook. We're on YouTube, and I'll be working all of those chats. And we have a team helping moderate those questions. We're going to wait until after the gentlemen are finished with their presentation in order to start asking questions. But please get them ready. Ask them as they come to your brains, and just enjoy the show. Please like, please share, please subscribe. We're ready to talk about functional safety.
Cool.
I'm
excited.
excited.
Thank you very much. So I guess to start us off, Jacob, could you define for the good people what a safety critical system is and what functional safety is as a whole?
Yes, indeed, I can. So when I was invited here to do a 10-minute talk about functional safety, it's a big topic to cover in 10 minutes. But just for people to get an understanding, functional safety is when we're talking about safety critical applications. And a safety critical application could be, for instance, a gas burner. So there you have a hazard of a gas leakage, and the gas leak could, of course, catch fire. It could explode. So there you have the safety hazard. If we're talking about other things, it could be like washing machines. If you're able to open the door while it's spinning, it could potentially take off your arm. Cars, you have drive-by wire, you have brake-by wire. So all of those types of applications are safety critical. So if there's any sort of words related to the application that would cause you to think, well, this could potentially be a hazard, that is likely to be a safety critical application. And to your second question about functional safety, we have defined a term being functional safety ready. And with functional safety ready, we use that for products that we think are more ready for functional safety applications than others. We have defined 4 main areas. First of all, of course, the product itself has to have the necessary features. So here we're talking about microcontrollers, so necessary functionality in the silicon for you to deal with the application and the safety. But we have 3 other very essential pieces. We have the FMEDA, we have the safety manual, and we have the functional safety development ecosystem. So those 3 are what we're going to talk about today, and those are essential for actually being successful with functional safety applications. So if we should look at these just quickly, the FMEDA, or failure mode effect diagnostics analysis, is a report that we make, and the report helps you understand the failure rates, or what we call failures in time, of the device, depending on what sort of functionality you use. You can imagine that you have your program in the microcontroller stored in the flash memory, and there could be a single bit fault in the memory. So those kind of things where you have a spontaneous or failure in the device is what this report is describing, and how that would affect your system. So you can calculate both the coverage plan and also the overall likelihood of a failure in that application. The other thing, which is a continuation of the safety manual, a continuation of the FMEDA, is the safety manual, and this is going into more details about the specific failure modes, how you can design diagnostics so you can actually discover those sort of failures in a systematic way. So you can say it's a user guide for you who are using a microcontroller in a safety application or a safety critical application. And the last piece we have on this slide is the development tools. As you can imagine, when you're doing safety critical applications, you want to make sure that all parts of your development chain is controlled. And if you have, for instance, a critical tool like a compiler that can affect the actual behavior of the product, it could, let's say that it compiles the code incorrectly, then that could be a safety hazard. And for that reason, we have our tool chain certified and qualified depending on which part of it you look at. And these, in combination with the safety manual and the FMEDA, is then a very strong basis for developing safety applications. And this is something that we can provide for all our 8-bit microcontrollers, the AVR and PICs, and is what you need to actually succeed doing such applications. So talking just a little bit more about the safety development tools, we have a number of key elements there. We have our IDE, which is certified for safety applications together with the compiler. And the compiler is the critical part here because, as I said, this is what can actually influence your end product. We have 3 different versions of our compiler, of the XC compiler. We have the XC8, XC16, and XC32, and all of those can be provided as safety certified tools in a special version.
Real quick,
the last
Jacob.
tool that I want to mention here. Yep.
So the microcontroller themselves aren't functional safety certified, right? It's purely the compiler and like the ecosystem surrounding it, right?
Yes, a very good point. So the microcontroller is basically it's a small computer, and if you imagine you're running a piece of program on a small computer, you would also understand that that software is an essential part of the safety of that application.
Right.
So the computer or microcontroller in itself cannot be certified. It's the system as a whole that you would actually certify. So the implementation, you can say. So if a customer is coming asking us for safety certified microcontrollers, we would say we can help you with all the collaterals, and that is why we have defined functional safety ready. And this is what you need to actually get easier through the certification process, and that would save you both time and money.
Okay. And so, like you mentioned, this is something that is available for all of our microcontrollers, but how do people tell what specific microcontrollers are recommended or functional safety ready?
So there we have on the product pages, we actually have an icon there. So on the slide here, you can see this hard hat icon. And if you see a product page that has this symbol, it means that we have all of these 3 pieces of collaterals. We have that ready to go. So you just contact us and we will provide it. So these are very valuable collaterals for us. And for that reason, you will not be able to download it directly from the web page. But if you contact us, we will provide the functional safety manual, and we'll provide the FMEDA, the compiler, something that you would purchase on our web page. You can also find more information if you go to the microchip.com/functional safety, either with or without the dash. That would take you to the general pages, and from there you can navigate through the different product families of microcontrollers and other products as well, and find the information that you're looking for.
Cool. So I think that's just about everything you wanted to cover. Was there anything?
I think you forgot to mention, Jacob, what about the diagnostic software, diagnostic libraries?
Exactly, Enrique.
Exactly.
There's one more thing.
And we have one more slide.
That is, and one more slide. That's true. So we have all of these. The FMEDA, the safety manual, is describing, should we say, the theoretical approach to how you do things. It's describing your failure rate, it's describing the mechanisms that you use to do the diagnostics, but we actually also have diagnostics libraries. And those are actually implementations of what is described as the diagnostics mechanisms in the safety manual. So with all of these items, you are very well prepared to design your safety critical application. You can get the libraries from us, you can get the FMEDA and safety manual, and you can get the tools that you need to actually develop there. So with that, you have everything you need to do safety applications, and that is what you should expect from a supplier of microcontrollers
Cool.
into safety applications.
Alrighty. So now this brings me to my favorite part of this show, the Q&A bit. Wayne, what sort of questions do we have?
Well, we actually have a couple of really, really good questions here. I'm going to
Nice.
try and gather my notes here because I have a terrible memory. All right, so this question is from from YouTube, and I'm going to mispronounce your name. I apologize, but M. Satya Durga Prasanna Babu asks, "What are standards to design safety critical systems?" And this is something that you guys, I think, kind of discussed briefly. But if you want to maybe spend a little bit of time elaborating, that'd be cool.
Yeah, there are several standards depending on what the type of application you're dealing with. If you're in an automotive application, you might have to work towards the standard ISO 26262. If you're on the appliance side, you might need to work with the IEC 60730. So, depending on what industry you are, there are different types of standards that basically you will have to comply with.
Right.
On our side, we basically try to, we are working towards, we're basically observing the ISO 26262 as being one of the most complete or one of the most stringent, and that way we can support the most customer types. So if we can supply an FMEDA, and that FMEDA you can actually use it for several types of applications, and independent of what industry you are working towards. I don't know if you want to add something to that, Jacob.
Yeah, it's true as you say, and then also to add for the development tools, we have certified those according to all the, what I would say to be the 4 major standards for our type of products: automotive, general electronics, appliances, and medical applications. So whether you do one or the other, that is a tool you can use. And as Enrique is saying, the strictest and most explicit standard is currently the automotive standard, and with the documentation from that standard, you'll be able to meet the requirements of the other standards as well.
Okay.
So
Cool.
we have also, for instance, Class B libraries, but those would be a subset of what we do for automotive.
That's
Nice.
awesome, guys. So let's see. I'm going to go next with a couple of comments. This is coming from all the platforms. They really love the slides, and they would love to be able to access the content on the slides after after we're done here with our live stream. So what we'll do is, and this is just for a programming note for everyone, what we're going to do is take these guys' slides and we're going to post them. We'll post links to them in the description of as many of the platforms as we'll allow, and we'll also have something featured on microchip.com/livestream after the fact as well.
Nice.
Next question is from Semi Asat, coming from Facebook, and the question is, can I use free RTOS in safety critical systems like medical? If not, why? Does that mean that free RTOS is not safe? Who wants to take this?
That's a trick question. because free RTOS has actually is not certified, it's not qualified for safety applications, but there is a variant of free RTOS which, if I'm not wrong, is called safe RTOS. It's a variant of free RTOS, and it's I think there's a commercial license with it, and that is I don't know if it's certified, but it's qualified at least for safety applications. So yes, there is a version of free RTOS that can be used for safety critical applications.
Okay, and that's called safe RTOS? Is that what you said?
Yes.
Okay.
Yes.
Mm-hmm.
Okay, perfect. Let's see. Fabian Romo wants to know if there are diagnostics available at the hardware level.
Yes, and actually, our safety manual describes some of the hardware safety diagnostic mechanisms. which depending on the type of device that you're using, can be as simple as the ECC. We have hardware CRC. We have some other hardware modules that can help you as a safety mechanism.
Okay. Let's see.
So just to supplement there, so Enrique is mentioning CRC, and I think there is a very particular feature that I want to mention there. So the CRC engine can actually, just to step back a little bit, in many microcontrollers there is a CRC engine, but the danger of that is that you have to initiate it through software. So you're starting up, and this CRC engine is meant to check your flash memory, but you already are executing from your flash memory. So you're depending on the flash which you are about to test. What we can do with the CRC engine that we have is that you can enable it through our fuse setting or our configuration bits. So you can do the CRC scan before the CPU is allowed to execute from the flash. And in that way, we have that mechanism in place. Of course, you still need from software then to verify that the CRC is working, but that is layers of functional safety that you actually have to test, verify that the hardware mechanism is working as it should. And another feature could be, for instance, a clock failure detection, where it would automatically switch back to an internal clock source if the external clock source is failing.
Okay.
Nice.
Perfect. Let's see. I have a menu of options here. So I'm not going to pronounce your last name because I won't get it correctly. But the first name is Michal. Do you have some kind of checklist tool to help with safety design and deployment quality? Who wants to take this one?
Yeah, so I can give a stab at that. I get the question is maybe from one that is learning functional safety, and my recommendation is to involve a consultant, a professional, and learn from that process, because some of these standards, they are, depending on which one you're looking at. If you're looking at, for instance, the automotive standard, is very demanding in terms of how you define your processes, your development processes. You need to follow the V model, the ASPICE process for software development. So it's not something which is trivial just to make a checklist and then you're done. But if you look at the standards define many of the specific things that you need to comply with, and what you need to integrate in your processes. If you're looking at other things, like the actual implementation, you get a lot of help with the FMEDA. The FMEDA is actually a table of functionality. So what you would potentially do is you'd look at your design, you would figure out what parts of my design are safety features, and how do you ensure that those safety features are operating correctly, and what sort of peripherals would that require in the microcontroller. And once you've identified that, you'd go to the FMEDA and you start picking those modules and figure out what are the recommended diagnostics for those specific modules. So to answer your question indirectly, the FMEDA is a very good document on a hardware level, but on the process level, it requires quite a lot more, and there you'd have to lean on the standards. And if it's your first design or one of your first designs, we recommend that you involve one of our design partners that are skilled in functional safety.
Yeah, bottom line is that functional safety should not be treated as a checklist. Okay, I did this, I did this, I did this. Okay, I'm done. I'm functional safety ready. But it involves a complete set of processes that you need to take into account to make sure that your application is functional safety compliant.
That's a great way to look at it.
Yeah.
Let's see. Mark Corominas asks, which ASIL level can we reach with your tools? And I think, Enrique, this might be up your in your wheelhouse here.
Okay. When we publish our FMEDAs and all the documentation that we have, we help our customer achieve certain level of ASIL. Within the FMEDA, and depending on the diagnostic mechanisms that you put into the device, there's a table on one of the one of the tabs of the document, where it actually tells you what ASIL level you can achieve or is possible to achieve with the safety mechanisms that have been implemented. We normally, when we polish our devices, when we polish all the collateral, we can tell you, okay, you're able to achieve an ASIL B, or you're able to, but that also depends on the application itself. So we cannot tell you that this device is suitable for it, or is certified to a certain level of
ASIL?
Yeah, so a certain ASIL level. But our documentation will help you determine if the device, with the safety mechanisms that you implement, both the recommended and whatever you choose to put into the device, actually is able to comply to a particular ASIL. So if you look at our FMEDAs with some of the standard and basic diagnostics, the table actually tells you that we can able to achieve an ASIL B. But then if your application actually requires an ASIL D, there are some techniques that you can use to achieve that. For example, ISO 26262 actually allows you to break up the safety level. For example, if you require an ASIL D, you can actually use 2 ASIL B subsystems to actually comply with that. I don't know, Jacob, if you want to add to that.
Yeah, so what we see in some applications is that to reach these higher ASIL levels, there's been a tendency to use specialized products. So let's just say tri-core special devices with a lot of expensive functionality. What we see now is that there is a trend to go towards, depending on the application, of course, but there is a trend to go to simpler solutions, which is to use standard microcontrollers, where you may have one primary controller, and then you have a secondary controller, which is helping with only the software, the safety portion of the application. And as Enrique mentioned, this decomposition into 2 different products means that you don't have as strict requirements for either of those, and they are much easier to implement. So with the documentation we have, we can, I was going to say we can guarantee, but it's very likely that you can reach what is equivalent to ASIL B. Depending on what functionality you need in the microcontroller, you can also get to ASIL C, but that is where we are sort of in a little bit of a gray zone, because it's depending on the auditor as well, what they see as sufficient ways of complying to ASIL C. ASIL D, you'd have to have specialized products if you need to do it in a single device, but otherwise you can do decomposition, which is both cost and development time effective.
Nice.
Mm-hmm.
Okay, so there's a couple of other questions, and we're going to try and keep this one a little shorter. So if we don't get to your question, you can actually ask us the question by sending an email to livestream@microchip.com, and we will route it through to the gentleman that we're talking to today.
And also, if I may,
yes,
we have
yes,
a very nice forum that we have just started. So there's not a lot of activity there, but we have just started up. And if you have questions, you can post them there so that everyone else have the pleasure of both the question and the answer. And we'd be happy to have a good discussion with you.
Absolutely.
There.
And I have actually posted the link to the forum in the chat, so and I'll repost it, and we'll actually add it to the description as well if you missed it.
Yeah, please take a look at that the forum. Right now, it does have quite a few entries on frequently asked questions as a starter point to start the conversation there as well.
Okay.
Nice.
So there's a couple of questions around artificial intelligence and FPGAs. So good news for you all. Clifford will actually be joining someone from our FPGA group in, I think, approximately, 4 weeks from now?
It would be.
So we'll stay tuned for that. We'll actually kind of discuss that topic. Of course, you can send us a question directly via email if you have something that's urgent. So we're going to go with, let's see. GMARF1 on YouTube asked if how do we ensure that our microcontrollers endure and survive a single bit failure?
Well, the idea of functional safety is not actually to prevent failures, but is basically to be able to catch and actually react to a failure. It's based on the premise that all electronics can fail.
Yes.
So yeah, we do have some reliability standards, and we have documentation as what to expect regarding to the expectation of a failure. But the idea of functional safety is what to do when a failure occurs.
Right.
The idea of functional safety is to be able to get to detect a failure and be able to get to a safe state on your application. If the microcontroller that's handling your brakes fail, you should, the computer and the automobile should be able to detect that failure and move to a safe state before anything bad can happen. That's the whole idea of functional safety. So that's basically the focus of it.
Perfect. And
and this specific example is quite interesting, because you can say in many systems, if we have a gas burner and the diagnostics are discovering a failure, you can shut off the gas valve. You can do certain things to enter a safe state. But if you have a car traveling at 60 miles per hour and you suddenly detect a failure in the steer-by-wire, you can probably imagine that that's pretty bad, and that's why the AC level for such an application is so high. And there you need to have redundancy, which is not only those failures, but are also allowing a safe progression of the system so that you can bring your car to a safe halt. But it would probably not allow you to restart the car after you've turned it on. You'd have to call for a service car there.
Mm-hmm.
Right.
yeah,
And that's your safe state. You're basically the car won't move. That's the safest.
that's also true. Yes. And to add to that, we actually do have, and this is a comment from Igor, one of our colleagues here at Microchip. We do have microcontrollers that do have ECC, which detect and correct single bit failures. Otherwise, you need CRC to detect the failure and then enter a safe state. So, we like to believe that we have things covered from both ends. So what I'm going to do right now is kind of close off here. We still have a lot of questions flowing in, but
Good.
our goal is to keep this fairly short. So just remember, if we didn't get to your question, you can ask us via email at livestream@microchip.com. Please tune in for the next coffee break, and I'm going to send it over to Clifford. You can talk about those.
Absolutely. So in 2 weeks' time, we'll be joined by Nick DeRosa, a Microchip employee who's going to talk to us about our design partner program, which is something that Jacob mentioned a little bit earlier. But to close things off, I'd like to give a special thanks to my two guests. Thank you, guys. Thanks to everybody behind the camera that made this possible. Thank you for tuning in. Stay happy, healthy. Tune in 2 weeks, and we'll see you later. Ready to shut it down.
Thanks, guys.